Good morning, students. Coming to the second module. In this module, we are going to discuss about the experimental determination of lowering of vapor pressure as well as elevation in boiling point. So first we will see what is meant by what are the basic requirements for the experimental determination of lowering of vapor pressure. So here I would like to mention the one process that is Ostwald's and Wacker's process. It is also called as gas saturation method or transpiration method. So here in this, first we will observe the experimental setup, and we have 6 bulbs which contains a wide amount of both solution as well as solvent, and these are kept in the some water bath to maintain the constant temperature conditions, that is thermostat. And we are passing through the air in 3 areas, and we also need some U-shaped tubes. So the three regions we need to pass the air, and first 3 bulbs are filled with the solution, and the next 3 bulbs are filled with the solvent, and which is kept in the thermostat, and then it is connected to the 3 U-shaped tubes which contains some solvent which can absorb these vapor molecules. If it is a water as a solvent in the solution and pure solvent, then here we can take the calcium chloride as the reagent in the U-shaped tubes. Means the air is passed through the solution and it absorbs some solvent molecules and pass through the solvent. It is also saturated with the solvent, and then it is absorbed. The solvent is absorbed by the dehydrating agent which is present in the U-shaped tubes. Then we can easily calculate the loss in weight of the solution in all the compartments. Then we can relate that one to the vapor pressure of the solvent and the solution. So this is the experimental setup. Then if you pass through this air to the first solution bulbs, then on the solution bulbs the surface has some amount of vapor molecules, and this air is saturated with that vapor molecules, and due to that the solution in solution bulbs, the amount of certain amount of solvent is lost and it is going along with the air. Then after sending to this air which is saturated with the solvent molecules to the solvent bulbs, here also the air already saturated with the solvent, again it is saturated with the solvent molecules present on the solvent bulbs. And after this air is passed through the U-shaped tubes. There your air it is saturated with solvent molecules of both solution as well as solvent, and here that air which contains water molecules, because here we are considering water as solvent in both solution and solvent bulbs, that water present in the air is absorbed by the U-shaped tubes and the air is passed as it is, and you will get the outlet of the air. And here we can observe some amount of loss of solvent, and also in the solvent bulbs also will observe some amount of loss in weight of the solvent. But in the in U-shaped tubes we can observe some gain of U-shaped tubes weight, because here it is lost in the form of vapor molecule and it is saturated with air, but here it is absorbed by the reagent. That's why here we will observe some weight increase in weight of the U-shaped bulbs. So all the 6 bulbs for the solution and solvent, also U-shaped tubes with the reagent, we should take weight prior to the experiment. Then coming to the calculation part, then loss in weight of solution bulbs, that is W1, is directly proportional to P, and loss in weight of solvent bulbs, that is W2, is directly proportional to the lowering of vapor pressure, that is P0 minus P. Then loss in weight of the solution bulbs plus solvent bulbs is equals to W1 plus W2, which is directly proportional to P plus P0 minus P. then W1 plus W2 is directly proportional to P naught, because it is plus P and minus P gets cancelled, and we'll get it mainly the loss gain in weight is directly proportional to vapor pressure of the pure solvent. And by dividing equation 2 by equation 3, we'll get this relation. This W2 means the loss in weight of solvent bulbs divided by loss in weight of both the solvent and solution bulbs, that is relative lowering of vapor pressure. And you can also loss in weight of both the bulbs, you can also easily compare with the gain in weight of calcium chloride U tubes. Then the relative lowering of vapor pressure is equals to W2 by W3, that is loss in weight of solvent bulbs upon gain in weight of calcium chloride U tubes. So now coming to the elevation in boiling point. So what is meant by elevation in boiling point? So before going to that one, we will see what is boiling point, how it is increased after the dissolution of non-volatile solvent. So boiling point is the temperature at which its vapor pressure becomes equals to the atmospheric pressure. Since the addition of non-volatile solute lowers the vapor pressure of solvent, in the previous colligative property we have seen clearly after the addition of non-volatile solute the vapor pressure of solvent is decreases. So it must be heated to at higher temperatures to make its vapor pressure equals to atmospheric pressure. So as the boiling point definition, according to boiling point definition, the temperature at which the vapor pressure becomes equals to atmospheric pressure. Vapor pressure of solvent becomes to atmospheric pressure, then only it starts boiling. So after addition of non-volatile solute to the solvent, vapor pressure of the solvent decreases. Then to equate the vapor pressure of the solvent to the atmospheric pressure, one should heat to a higher temperature, so that we can get the we can equate the both the pressures, and hence the boiling point of the solution. Hence, solution boiling point is always greater than the solvent boiling point, and that is denoted by delta TB, which is equals to Ts minus T0. Ts means the boiling point of solution and T0 means boiling point of pure solvent. This one we can clearly observe by using vapor pressure temperature curves, and here by taking a pure solvent and solution 1 and solution 2. So solution 1 contains some amount of concentration, some x grams of solute into the pure solvent, and in solution 2 some 5 grams of solute after dissolving in solvent will get solution 2. So here we'll get the relation like this. This is the vapor pressure and this is the temperature. And for the pure solvent, so this is the vapor pressure of the pure solvent and its boiling point is T0. So in pure solvent case, the curve or the relation between vapor pressure versus temperature is like this. That is AB. As the vapor pressure is equals to atmospheric pressure, this P0 is also equals to 1 atmospheric pressure. It is equals to atmospheric pressure, then it starts boiling. That point is T0. So this point is T0, that is boiling point of a pure solvent. And this is the pure solvent curve. And if we add some x grams of non-volatile solute to the pure solvent, then the vapor pressure from P0 to P1 it is decreases due to the evaporation in the surface phenomenon. The vapor pressure is decreases from P0 to P1. But the boiling point is increases from T0 to T1. So because the vapor pressure is decreases up to here, but this vapor pressure is not equals to the 1 atmospheric pressure, that is atmospheric pressure. So to equate this pressure to this one, the solution 1 case, we need to increase the temperature. So at this point, it is equals to the vapor pressure of the solution 1, it is equals to atmospheric pressure, and hence the boiling point is greater than the pure solvent. The same way in the solution 2 case also, So the vapor pressure is further decreases after dissolving a Y grams, that is from P0 to P2. So as we, according to boiling point definition, the vapor pressure should be equals to atmospheric pressure. So to increase the vapor pressure, we need to increase the temperature from this point. So that's why after equating this vapor pressure of solution 2 to the atmospheric pressure, so it starts boiling. Means the temperature of the solution 2 is further increases. So this is T2 is the boiling point of solution 2 and T1 is the boiling point of solution 1. And T0 is the boiling point of pure solvent. So from this vapor pressure temperature curves, we can get the relation, that is T1 minus T0 is equals to delta T1B. That is elevation in boiling point for the solution 1 and pure solvent is delta T1B, and elevation in boiling point for the solution 2 and pure solvent is delta T2B. And after observing these curves, this GH, the GHJ and GIK are almost equilateral triangle, so that we can get the relation like this: GH upon GI, GH upon GI is equals to GJ upon GK. So GH refers to T1 minus T0 upon GI refers to T2 minus T0, which is equals to GJ means P0 minus P1 upon GK means P0 minus P2. So this relation will get by using vapor pressure temperature curves. Then we can generalize the above relation as delta TB is directly proportional to lowering of vapor pressure. That is, elevation in boiling point is directly proportional to lowering of vapor pressure. So then by using elevation in boiling point, we can also get the molecular weight determination, or we can also calculate the molecular weight. So according to Raoult's law, we already derived this in the previous module, that is P0 minus P upon P0 equals to weight by molecular weight of solute into molecular weight of solvent. Then if you rearrange the above equation like this, P0 minus P equals to this number of moles of solute to solvent into vapor pressure of pure solvent. Then molecular weight of solvent is constant and P0 also constant for a given temperature. Then above equation becomes lowering of vapor pressure P0 minus P is directly proportional to W1 by M1 into W2. So from vapor pressure temperature curves for the boiling point, elevation in boiling point, we have the relation P0 minus P is directly proportional to delta TB. Then we can substitute in the place of lowering of vapor pressure. So we will by delta TB, then we'll get the relation, that is delta TB is directly proportional to weight of solute by molecular weight of solute into weight of solvent. Then delta TB is equals to, if you remove the proportionality constant, Kb into weight of solute by molecular weight of solute into weight of solvent. Here Kb is called as ebullioscopic constant or boiling point constant or molar elevation constant. So if the molarity is 1, then the delta TB, that is elevation in boiling point, is equals to the ebullioscopic constant, that is Kb. If the elevation in boiling point produced by dissolving 1 mole of any solute in 1 kg or 1000 grams of the solvent, then delta TB equals to Kb into M. So M here, M refers to molality. So this is the relationship between delta TB, that is elevation in boiling point, and molality. And if the weight of solvent is given in grams, then equation 4 becomes delta TB equals to Kb into weight by molecular weight of solute into 1000 by weight of solvent. Then by above equation we can calculate the molecular weight of solute, that is M1 is equals to Kb into W1 by delta TB into 1000 by W2. So all these abbreviations of all the equations The Kb is a characteristic of a particular solvent. Kb equals to RTB square by 1000 into LV, where LV is the latent heat of vaporization and TB is the boiling point of the solvent in absolute scale. And here we already discussed in the first module itself, all these colligative properties are interrelated. We can get the relation between these two. So by taking the elevation in boiling point formula, that is delta Tb equals to Kb into weight by molecular weight of solute into 1000 by weight of solvent. Then number of moles of solute equals to W1 by M1 and number of moles of solvent equals to W2 by M2 and weight of solute equals to number of moles into molar mass of the solute and weight of solvent equals to number of moles into molar mass of the solvent. Then in the above equation, if you substitute number of moles of solute, that is N2, in place of W1 by N1, in the place of W by 1 by M1 place the number of moles of solute, and in the place of W2 N2 into M2. So then we'll get the equation delta Tb equals to Kb into 1000 into N1 upon N2 into M2. Then if you take the number of moles aside, then we'll get the relation like this. Then we already know that delta Tb is equals to Kb into 1000 by M2 into N1 upon M2. But according to Raoult's law, relative lowering of vapor pressure is equals to N1 upon N2, that is W1 by M1 into M2 by W2. Then if you substitute this N1 upon N2 in the above equation, then we'll get delta Tb equals to Kb into 1000 by M2 into P0 minus P upon P0. So this is the relation between relative lowering of vapor pressure and elevation in boiling point. Thank you.